Hi, this is Mr. Manley, and in this video I'm going to look at solving equations with logarithms. The first thing to review before we solve these equations is the definition of a logarithm, which is that if I have log base a of b is equal to c, and I'll say if, then it would be true that a to the c is equal to b. And this is what everything comes back to. So you should write that down, review that, and as we go through the few problems here, you're going to see that I keep applying this principle again and again. The other thing that we're going to look at, that we're going to use, are the properties of logarithm, and those are the product property, the quotient property, and the power property. And you can review those on your own or find those, but those will get some application in solving these equations. So here's the first one. The thing before we apply what we know about logarithms, we need to isolate the logarithm. So I want to use this idea of log base a of b, but I don't have that over here. I've got log base a of b, but I've also got this -7. So before I apply what I know about log base a of b, I have to isolate the expression. So in this case, I'm going to divide by -7, like so, and that'll give me log base 5 of 4x is equal to 2. Now I can apply the definition of a logarithm, that I have a log base a of b equal to 2, then it's going to be true that 5 squared is equal to 4x. And from there, I can easily isolate 4, and I'll leave the rest to you. It's just 25 over 4, right? Now we will look at the same problem, but with a natural log. Same situation. I need to divide by 3 to isolate the log expression. And again, just coincidentally, I end up with ln x plus 5, and I end up with equals 2 again. So that happened here. I ended up with equals 2 in here, but that's just a coincidence. We could end up with anything on the right side. And remember that in order to apply the definition of a logarithm here, I'm remembering that the natural log is base e, log base e. Therefore, I can write this as e to the second, that is taking my base of the logarithm, which is e, and then raising that to the second power, equals x plus 5, and therefore x is equal to e squared minus 5. There's nothing else that we want to do with that. I suppose you could be asked to find a decimal approximation, and given a specific number of significant digits that you want to round off to, but here I'm just going to leave this as x squared minus 5. All right, now we're going to get an opportunity to apply the properties of logarithms. I want to get to that single statement of the log base a of b. And I just want to have a single log base a of b. Clearly, I don't have that here. I've got a log and I have another log. But we can bring these together to the same side of the equation. And it would be equal to 1. And now perhaps you can see that we are set to apply the product property of logarithms, where I can multiply the two arguments. So x minus 2 times x minus 5 on the left side there. And now I've got the log base A of b equal to c. And my b here, so the b value is all of this. All of that is the b value. So let's apply the definition of a logarithm now. Therefore, we can say that 4 to the first power is equal to this x minus 2, x minus 5. Well, how do I solve from here? Hopefully I recognize that I could have a polynomial, and the way that I solve a polynomial is by setting it equal to 0. So we're going to have to do a little bit of work to do that, just expanding this by doing FOIL, and then I want to set it equal to 0. I'm also going to reflect it just for convention's sake, so x squared minus 7x, and then when I subtract the 4, I'll have 10 minus 4, which is 6, equals 0. We're solving for x here, so I'm going to factor again. X looks like minus 6 minus 1. Now, I would expect that the ones that you encounter here will work out conveniently and you'll be able to factor them. If you were not able to factor it, of course, if it's a quadratic, you could use the quadratic formula. But where we're at here with these factors, we can use the zero product property and say x equals 6 or 1. But we have one more thing to check here. We've got to check if these are in the domain. I got to make sure that that will work here and that will work here. And what I'm really looking for is, will I end up with an argument? And let's say that term is the argument. The term argument is referring to this part of the expression. And what I want to know is the argument negative? Because if the argument is negative, I can't do that. Like say, let's just look at the most basic case here. If I go, what's the log of negative 1? So that's saying to what power is 10 raised to get negative 1? And can you think about that for a moment? That there's no way I can raise 10 to a power that'll make it flip over to negative. You might want to raise it to a negative power, but that won't make the output negative. That'll just make it the reciprocal. 10 to the negative 1 is 1 over 10. It's not negative 10. It's not negative 1/10. So there's no way that I can have a response or that I can evaluate an expression that has a negative argument for the log. Now, going back to our case here, you see that when I plug in the 1 here, I get 1 minus 5 is negative 4. So that solution is no good. I'm going to drop that. Now, if I try the 6 here, I'm going to have 6 minus 5 is 1. And if I try the 6 here, I'm going to have 6 minus 2 is 4. So understand that after all of the work and you get down to the bottom and get your solution, you still need to check and make sure that those solutions are in the domain. The domain being values of x where the argument will be positive. Okay, here's a new thing. We don't have a log. Now remember that we began with this idea that we know that log base A of b is equal to c can be written as a to the c is equal to b. All right, we're going to go backwards. So we've been going from here to here. Now in this case, we're going to go from here to here. And this will allow us to solve for the logarithm. So let's go ahead and try that. I'm going to go log base 5, because the base of my log is going to be the same as the base of my exponential expression. And then log base 5 of c, which in this case is 12, is equal to 7x. And solving for x, simple enough, 1/7 log base 5 of 12. It may be that you're expected to enter the solution in exact form. If you're given a decimal form and told to round off to the nearest hundredth or the nearest thousandth, you'll have to use a calculator. In that case, you're going to use the change of base, probably. There are calculators that will do base 5, but that would be a very advanced calculator if you have that. The calculator that you probably have is going to require you to convert it to base 10. And by the change of base rule, I can change log base 5 of 12 to log 12 over log 5. Then I could enter that into the calculator and get the decimal approximation. Now here's a very challenging one, and let's take a look at this. We have two sides that have a variable exponent. So when I try and do my log base 8 of 9 to the negative 5x is equal to negative x plus 10. So if you need to, go ahead and pause and see the application of the definition of a logarithm, how I took log base a of c, or log base a of b equals c, and I converted that, or I converted to that. I started off with a to the c equals b. With that said, now I'm going to use the power property of logarithms. The power property says that the negative 5x can become the coefficient of the log expression. And then from here, it's really pretty basic algebra. It looks very complicated, but I'm just going to combine like terms, essentially. Or you might think about it as factoring. So I'm going to add x to the left side, like so. And that'll leave me with a 10 here. All right, I want to solve for x. Can you see what to do here? To solve for x, I'm going to factor the x. Like so. And then it's a simple division. Divide by this factor and divide this side by that factor. Cancels, cancels, and I get x is equal to this. Again, it may be a calculator entry if you're asked for a decimal approximation, or it may be that you're going to enter it exactly. For my part, I'm more interested in the exact response. One more thing to look at. After all we've talked about with logarithms and variable exponents and using the definition of a logarithm, we don't need to use that here. We could, and it would work, but what we see here is that I can change these to a common base. And this would be a basic type of problem that you do see in algebra. Maybe you haven't seen it for a while. Maybe you saw it in Algebra 2. Maybe you remember, maybe not. But you see that I can change to a common base of 2. So before going through this big process here, where I have two variable exponents, and I'm using the log, and then I am having to combine like terms and factor, before going through that whole process, you do want to check, is it possible to write these in a common base? For 8 and 9, it wasn't possible, but for 16 and 2, it is. So from here, I can simply apply the laws of logarithms, power to a power. I have a power to a power, so I multiply those. 16x plus 4. And then by the, actually it's the one-to-one property, one-to-one property, which says that if I've got these common bases here, then I can solve the equation by setting the exponents equal to each other. So I can solve for x here by setting 16x plus 4 equal to 12x. And then that's a pretty easy, that's a very simple equation solved there, and I'll leave that for the student. So that's many types of problems that we can see with solving for equations with logarithms or with a variable exponent using the definition of a logarithm.